Okay, let's talk about the factor theorem. Factor theorem says if you got yourself a polynomial, then some number k is a zero of that polynomial if and only if x minus k is one of the factors. Now, this can be extended using what's called the fundamental theorem of algebra that we'll talk about in another video that will say that every polynomial, even though you learned back in college algebra, oh, well, this guy doesn't factor. Yes, it does. It just doesn't factor easily. Every polynomial factors, and the degree will tell you the number of factors. And every one of those factors is of the form x minus a root. So if our degree is 10, we will have 10 factors, not necessarily distinct. You might have a bunch of repeats in that list. We'll have 10 roots. We won't necessarily have 10 x-intercepts because we might have repeats, or we might have complex roots. Roots can be complex numbers. But all we're talking about here is the factor theorem that just says roots and factors go together. If you know a root, you know a factor, and vice versa. Okay, so here we've got some polynomial. First, we want to show that x plus 2 is in fact a factor. Well, we could just go through the work of factoring this guy, but he's hard to factor. Like there's no easy way to just factor this from first principles. But we're told we think this is a factor. How do we show that? By showing -2 is a root. What's it mean to be a root? A root makes the function 0. So we could have just plug -2 in here. Why -2? Because remember, the factors are always x minus the root. So I'm looking at this as x minus -2. So you could try this on your own, plug -2 in here and see you'll get 0. Another way to do that is to show that you get 0 on long division if we were to divide this guy by that factor. Well, remember we learned in one of the previous videos, a quick way to do long division is to do synthetic division. So we've set up our coefficients here from our polynomial. The guy we're plugging in, it's always x minus the one we're interested in. So -2, that's x minus -2. Bring down the first one. Multiply. -2 times 1 is -2. Add straight down. Multiply. Add straight down, and so forth. Hey, look, we got 0. If you get 0, then that means you've got yourself a 0 or a root of the polynomial. The factor theorem says then this must be a factor of this polynomial. Now, because we did synthetic division, see, here's another advantage of doing synthetic division. We didn't just prove that -2 is a root. We could have just plugged in to do that. What we've also done is we've started factoring it out. I know what we will get if we divide this polynomial by x plus 2. This will be our quotient. And remember, we started with third degree, so this will be a second degree polynomial. That's the remainder there. I like to box him off. So look, that means this guy here factors as x plus 2 times, look, here are our coefficients of that quadratic. Now we're down to a quadratic. Now that we've got a quadratic, we just factor. Worst case scenario, once you get down to a quadratic, you use quadratic formula to find the other roots. So this is the approach we're going to take with polynomials. We're going to use what's called the rational root theorem to guess at some of our roots. We're going to check if they are roots using synthetic division. If they are, if we get a 0 here, then we've now reduced our polynomial down to some linear factor times something that's smaller than what we started with. And we repeat that until we get to a quadratic, and then we either just factor using intermediate algebra factoring, or we use quadratic formula to get our last two roots. Okay. So here, I want to find all the roots. I want to find all the zeros. They told me that 2 was one of my roots. That's what this says. 2 is a root, also known as a 0. Those mean the same thing. Why? Because x minus 2, they said, is a factor. The factor theorem says that these mean the same thing. These always mean the same thing here. That's just definitions. Root and 0 mean the same thing. The factor theorem says that these are the same piece of information. How are we going to check that? A couple of different ways. We could just do f of 2. So that'd be 2 cubed plus 4 times 2 squared minus 4 times 2 minus 16. We could probably do that in our heads. You're going to get 0. But that doesn't help me find the other roots. So if we factor this out, we could do long division. I could do absolutely nothing wrong with this. Some people prefer this, in fact. You're always allowed to just use long division here, divide it all out. Whatever you get up here is now going to be a quadratic because it's always 1 degree less than what you started with because we're dividing by 3 minus 1 will be 2. But I'm going to do this using synthetic division. So I'm going to write all of my coefficients, making sure I don't skip over any powers of x. 1, 4, -4, -16. We didn't have any missing powers of x, so I don't have to put any zeros. Here's where people mess up. The number outside here is whatever's after the minus here. The thing that we think is a root. First one just comes straight down. Then it's multiply and add the rest of the way. 2 times 1 is 2. 4 plus 2 is 6. 2 times 6, 12. We get 8. 2 times 8, -16. Oh boy, look at that, 0. If we didn't get 0, we know we goofed. What's left over right here are going to be the coefficients of my polynomial that's 1 degree less than this guy. So this means x cubed plus 4x squared minus 4x minus 16 can be factored. X minus 2 is one of the factors. And then my quadratic factor will be 1x squared plus 6x plus 8. And we're going to keep going until we get all linear factors. This guy factors again. Like you should be able to do that in your head. That's x plus 2, x plus 4. 2 times 4 is 8. 2 plus 4 is 6. So now I have completely factored that polynomial into 3 linear factors. He was 3rd degree. He had 3 linear factors. He has 3 roots. My roots, also known as zeros, will be 2, -2, and -4. We want to think of these as x minus the root. Because if I plug in -2, -2 plus 2 is 0. If I plug in -4, -4 plus 4 is 0. And that's a good place to stop.